In this video, we're going to look at how to solve inequalities. Let's start with just a very basic inequality, x plus 3 greater than 0. So if we want to solve this, this is very simply, we're going to subtract 3 over, and we're going to have the x's greater than negative 3. Probably have seen solving linear inequalities several times. They're relatively simple. We want to solve a little bit more complex of a problem. Let's take another equation. Let's take x squared plus 3x plus 2 greater than or equal to 0. This one's a little bit more complex because we don't just have a linear equation, we have a quadratic equation. In order to solve our inequalities, the first thing we need to do is find our boundary points. So in order to do that, we are going to, in this case, factor it in order to get the zeros. We want to have the boundary points, which we can think of as zeros in this case, or as we're going to see in other cases, they could be vertical asymptotes as well. Vertical asymptotes VA. So to find my zeros, I'm going to factor. Whenever possible, factoring is easiest. So we'd have x plus 2, x plus 1. And so to get our zeros, we would set both of these factors equal to 0. And we get negative 2 and negative 1. Now, unlike linear inequalities, I can't just set both of my factors equal to 0, greater than or equal to 0, as I did for the last equation, the last simple linear inequality. I need to do an inequalities table. I need to set up an interval table. So this is going to allow me to determine which regions actually work. So in my interval table, I'm going to have intervals. I'm going to look at test values, which I'm going to call TV. And then I'm going to try and determine whether that region works or not. And I'm going to do that by looking at the sign based on the test value. So let's just illustrate this. My first boundary point was negative 2. Negative 2 comes before negative 1. So that's where I'm going first. Because I had a greater than or equal to right there, I can include that negative 2, so I'm going to use a bracket. And I'll have negative 2 to negative 1, same idea. Because I can have it equal to 0, I'm going to use a bracket once again. And then I'm going to go from negative 1 to infinity. Test value is just a point inside each of these intervals that's going to allow me to test to see whether I actually have something that's greater than 0 or not. So let's say negative 3 falls in that first region. I could have put negative 10, negative 20. Really, there's an infinite number of values that have worked. In between these two values, in the second interval, negative 2 to negative 1, I have to be a little bit more careful. So negative 1.5 would work in that region. And then something greater than negative 1, well, 0 is always a nice, easy test value whenever possible. I can always take these test values and stick them back into the original equation, or it's a lot of times easier to plug it back into the factored form. And the reason for that is then I just have to keep up with signs. I don't care about the value as much as just the signs. So if we have negative 3 plus 2, that's a negative. Negative 3 plus 1 is a negative as well. So we have our two negatives here. A negative times a negative is a positive. So I know my sign down here in the table is going to be a positive. Negative 1.5. Negative 1.5 plus 2 is a positive. Negative 1.5 plus 1 is a negative. A negative times a positive is a negative, and that's why I have my negative in my second row here. Finally, 0 plus 2 is positive. 0 plus 1 is positive. And so positive times positive is positive. Plugging into that factored form is easier than the first equation because all I have to do is keep up with those signs. And now I can go through and say, well, which ones are actually greater than 0? Well, the positives, that first and the last. So my answer would be negative infinity to negative 2 in a bracket. Union, we're going to use that union sign again like we did with domain, negative 1 to infinity. And there would be my solution. So what we cannot do, like I said, is just set each of these factors, I'll underline them in blue, each of those greater than 0. Because in that case, you're only saying, well, either or of these could be greater than 0. If this one's greater than 0, but this one's not, that's still going to be a positive times a negative, which is not going to allow my inequality to work. That's why we must set up our interval table. We could also think about this in terms of a graph. X squared plus 3x plus 2, we know what that looks like graphically. That is a quadratic function that's facing up with a y-intercept of 2. And so at some point, we knew it crossed at -2 and -1. At some point it's going to cross that y-intercept. We wanted the parts greater than 0. That would be everything from -2 and less, and then everything from -1 and greater. Those two regions there, we'd end up with the same solution, -infinity to -2, and then from -1 to infinity, same as we got before. That's definitely a little bit easier. The reason we don't do that strictly is because sometimes we have a little more complex of a function. We don't necessarily know what the graph looks like right away. So setting up that interval table will always work. We can always set up that interval table to test out our answers. Let's take another one. Let's take a degree 3 polynomial, x cubed plus 16x squared is greater than, this time we'll just use greater than -48x. So once again, I need to start by getting those boundary points. I'm going to have to factor this if possible. In order to factor it, whenever I see anything that's nonlinear, I need to get it set equal to 0, or anything polynomial that's nonlinear. I need to get it set equal to 0, or because we have an inequality here, we're going to get it set greater than 0. But the key is we want to have the 0 on that right-hand side. At this point, we are going to be able to factor this. We can factor out that x first. So that leaves us x squared plus 16x plus 48 greater than 0. And finally, we want to factor what's inside those parentheses. So we're going to have x plus 12, x plus 4. And so we get boundary points of 0, -12, and -4. So next we'll do our interval table. My intervals, -infinity, -12 was the smallest value. And this time I'm using a parenthesis and not a bracket. Let me clean that up a little bit. Because I want it to be strictly greater than, I don't want to allow for it to be equal to. So we're going to have a parenthesis over there. Next we're going to go from the -12 to the -4. Again with the parenthesis, and then from -4 to 0, and then finally from 0 to infinity. So we have one more interval this time because we had an extra 0. Next, think about our test values. I could pick, say, -15, doesn't matter. Something in between -12 and -4 would be -5. Something between -4 and 0 would be -1. Something greater than 0 would be 1. We're going to plug these in. I'm going to plug them into this last factored line down here just because that's going to be easiest. So -15 is obviously negative. -15 plus 12 is negative. We have a negative. So as far as our sign there, we're going to have a negative. -5 is going to stay negative. That one will be positive. That will stay negative. That's going to be a positive. -1 will be a negative, positive, positive. Negative times positive is a negative. Finally, the 1, they're all positive, which means this is a positive. We wanted, once again, the positives because it was greater than 0. So we're going to have -12 to -4, and then 0 to infinity. Notice every single time our signs have alternated because we had a multiplicity of 0 on each of those roots. If we took something that looked like this, x minus 2 squared greater than 0, once again, this is a quadratic equation. Let's change it to a less than 0 for a change, just to see a difference. We know our boundary point is going to be x is equal to 2. So when we set up our interval table, what we're going to notice, because that 2 had a multiplicity of 2, it is quadratic, it has a multiplicity of 2. We'll have -infinity to 2, and then 2 to infinity. When we pick our test values, we should notice that the signs do not alternate around that number. So for instance, when we plug 0 in, 0 minus 2 is -2. When we square that, it's a positive. The sign is going to be a positive. And 3 minus 2, that's also 1. That's a positive. So for the first time, notice the signs are positive, positive, unlike the last case where we had negative, positive, negative, positive, and we had, back in the first, positive, negative, positive. The sign stayed the same on the last because we had that multiplicity of 2. Well, that makes sense because we know anytime we have multiplicity of 2, it means it's touching our axis and turning around. We're not actually passing through that value. So here, we wanted the ones that were less than 0. There's never a time we're less than 0. We have no values that have a negative sign here, and so we have no solutions. Finally, I want to look at one last type of inequality. As I said, we can apply this to any type of equation. Let's take x plus 3 over x minus 1 greater than 0. So here we have a rational inequality, have a rational equation. So our boundary points, we're going to have to think about the zeros, and we find those by setting the numerator equal to 0. X plus 3 equals 0 is going to give us negative 3. We also have to think about our vertical asymptote value, and there we get x is equal to 1 because we've set the denominator equal to 0. Those are both going to be values in my interval table. Both of those are going to be boundary values. Negative infinity to negative 3. We have the equals to bar, so we can include the negative 3. From negative 3, we're going to go to the 1. 1, even though we have the equals to bar, remember, what is the definition of a vertical asymptote? That's a value that we can't have. We can never include a vertical asymptote, so it's going to be a parenthesis. And then from 1 to infinity. So the 3 is included because of the equals to bar. We can have 0. The 1's not included because it's a vertical asymptote. Vertical asymptotes are never included. Next, we'll pick our test values, negative 4, 0, 2. And then finally, we'll look at the sign. So we can always do the inequality the full way out. We can think about negative 4 plus 3 is negative 1 over a negative 5 and have a 1/5. But it's always fastest just to think about the sign when possible. So we'll have a negative 4 plus 3, that's a negative. Negative 4 minus 1, that's a negative. Negative over negative is positive. 0 plus 3 is positive. 0 minus 1 is negative, so that's a negative. 2 plus 3 is positive. 2 minus 1 is positive, so that's also going to be positive. We wanted the positive regions, the ones greater than 0, so our answer will be negative infinity to negative 3 in a bracket, and then the 1 in parentheses to infinity. So no matter the type of function, whether it's quadratic, cubic, some higher degree power, or rational, or it could be something like an absolute value, we can always set up the interval table. We can always just compare the signs if it's a rational or polynomial function, or we could have actually thought about, well, what is the value of this? What does this thing give us? Is that greater than 0 as we desired, or is it not? But here we took a shortcut, we looked at the sign. But we must set up the interval table. We cannot just use a shortcut of setting x plus 3 greater than 0, x minus 1 greater than 0. That will not work. We must set up the table in order to get these solutions. Please let me know if you have any questions.